Computing session with Winston Saunders as our moderator.
Hi, my name is Winston Saunders. I'm board member in the Green Group and here today to help lead a quick discussion, or today's discussion about exascale high-performance computing efficiency. So what I'd like to do, we've got a great selection of panelists here. I'd like each panelist to just briefly introduce themselves. Each person's brought just a few slides to introduce some of the concepts around the efficiency challenges we have to meet exascale high-performance computing goals. And after each, we get quickly through the presentations, the introductions of ideas, what we'd like to do is open the discussion up for audience questions. So please make notes and think of those great questions as you hear the topics. Let's go ahead and first introduce our panelists.
Okay. My name is Wu Feng. I'm from Virginia Tech. I'm a faculty member there in the Department of Computer Science, Electrical and Computer Engineering, and the Virginia Bioinformatics Institute. I'm also the founder of the Green 500, which seeks to rank the most energy efficient supercomputers in the world. And that was a project that stemmed out of some earlier work on an energy efficient computer called Green Destiny, which was a 240 node supercomputer in 5 square feet that consumed 3.2 kilowatts of power, roughly equivalent to 2 hair dryers. And this was over 10 years ago, before being cool was cool.
Okay, Terry?
Hi, I'm Terry Quinn. I'm from actually just up the road, about 40 miles that way, at Lawrence Livermore National Laboratory. We're a Department of Energy laboratory. We've been in computing simulation for 60 years. In fact, the first year we opened in 1952, we got a UNIVAC 1 and actually had to install air conditioning the first time on our site for that. So we've been in simulation a long time. Today we have about 28 petaflops of computer on our floor, and we helped along with IBM to fund and develop the BGQ, which is a very energy efficient technology that we're deployed right now.
Hi, I'm Alan Lee. I'm the Corporate Vice President of Research and Advanced Development at AMD, or Advanced Micro Devices. Been there about 5 years. My background is in mathematics. Spent time at some other companies as well, but I got into supercomputing a few years ago when I was running a company which is doing private equity analysis of a variety of different forms.
George?
My name is George Chu. I'm from IBM Thomas J. Watson Research Center. I'm senior manager of the Blue Gene supercomputer. And I've been with Blue Gene since day one. The 3 generations, we worked together very closely with the Lawrence Livermore National Lab. And since day one, we talked about energy efficiency.
Good afternoon. My name is Deva Bodas. I work for Intel. I've been focusing on energy efficiency for last about 13 years. In fact, and I essentially work on servers and high-performance computing systems. 13 years ago, actually, I realized there are going to be power challenges, cooling challenges, and I started convincing Intel that on servers, we need to pay attention to power. And the rest of the industry took a long while before everybody to realize there are issues. Similarly, we used to talk to the customers in high-performance computing, and again, the approach was, I can throw in money, I can get as much as power, I don't care about the power. I think last 2 years, the tune has started changing, so paying more attention to that, and there are some interesting challenges that we all talk about here.
Great, thank you. All right, so now we'll move into our presentations. So each presenter has just a few slides to introduce the topic and their specific concerns in the exascale computing area.
Okay, thanks, Winston. I'm going to talk about this from the perspective of more an analytical perspective or end user perspective, and then you'll see more later on with respect to where technology and the vendors are going with this. So this is a perspective from the Green 500. So if you take a look at the lists, trends from when the Green 500 started, you see the following plot. On the y-axis is megaflops per watt, performance over power. And on the x-axis, you see each instantiation of the Green 500 list. And what's interesting to really note here is that this is a box plot. And so the first the second and third quartiles are effectively inside the green boxes. The first quartile are all the outliers that go above that box, and the last quartile is below the green box. Okay. So what's interesting to see with respect to the Green 500 in terms of the energy efficiency in megaflops per watt, what we're seeing is that the top end of the list, the first quartile, the energy efficiency is improving exponentially. However, if you take a look at the median, or where those box plots, the box parts are, the second and third quartile, the energy efficiency is only improving linearly. Okay, so that's the striking thing that you see with respect to the Green 500 data that we have thus far that has tracked over the last 5 years. So I wanted to set the stage for that context and bring up this exascale computing study, technology challenges in achieving exascale systems. And this is from a study done by DARPA, and it's noted at the bottom, exascale computing study, technology challenges in achieving exascale systems. And one of the goals here is effectively to reach 20 megawatts for an exascale computing system. Because that was thought to be such an aggressive goal, the thought was that maybe a more realistic projection would be shooting for something along the lines of 67 megawatts. A more conservative projection that is also mentioned in the study is a target of 100 megawatts. So on the next slide, what you're going to see, on the next slide, you're going to see where the projections are between the 20 megawatt very aggressive projection and the 100 megawatt conservative one, and the 67 that will be in the middle. So you'll see this in the next slide. Here are the trends. On the y-axis, we have the power consumption, and the x-axis, we have the energy efficiency in terms of megaflops per watt, and these are on log scales. And what you see, actually, I guess I should point. Can I point? Nope. So, whoops. Let's go back. So what you see here, if it goes back one more, nope. Okay. So that was the number one machine that you see up there on the left that here, that in terms of extrapolating out to 20 megawatts and 100 megawatts, we're already pretty high up there in terms of the power consumption. So the only thing that we have to twiddle with along this dimension is trying to make the systems more efficient, because we're generating so much power already. If we take it from the perspective of this machine down here, which was the most recent machine that was at the top of the Green 500, you see that we're very efficient there, and there's a more, if you will, ceiling to grow out to the 20 megawatts and 100 megawatts targets. If we take a zoomed view of this, you'll see this is a zoomed view of just the November 2012 list. Okay, so actually, one only thing I do is go back real quick. So I'm going to take a zoom view of the 2012 list, and that's the dots that are kind of this purplish color. Okay. So we're going to take a zoomed view in this region down here on the next slide. And what's interesting to see right now, I think it's pretty interesting, is if you take a look at the efficiency, these are the most efficient supercomputers in the world right here. And then below a gigaflop per watt or 1,000 megaflops per watt are the rest of the machines. And if you look over here in this right-hand column, this is dominated by heterogeneous computing environments, which is these aqua-colored ones. The only homogeneous machine that's over here beyond 1,000 megaflops per watt is the Blue Gene Q machine, and that's this vertical line of triangular points in that graph. And just about done here. So this is a plot to extrapolate to exaflop, and so what I think is interesting here is we take this line and we extrapolate the top machine on the Green 500 and the top machine on the top 500 list, and we extrapolate it out to an exaflop, and an exaflop Blue Gene Q would be 493 megawatts, and the number one machine extrapolated out to exaflop is 1.2 gigawatts. So
John's drooling at the thought of that.
the thing that I think is the tongue-in-cheek thing is that if you took this line that we had here and we fit a line on here, and if you continue to extrapolate it out, by 2018, we would actually be generating power instead of consuming power. However, you notice that this stops in October 11th. Now, if I take a look at the next two instantiations of the list, and this is my last slide. So I just added these last 3 points here. You see it all flattened out now. Okay. And so we hit the asymptote. It was looking really rosy about 18 months ago, and we hit the proverbial wall at this point. And so these numbers here, this is, whoops, and that, I just passed through it, but that got us to, we're still going to be projected about 450 megawatts in terms of exascale.
Okay, great. Okay, now I just noticed that our slides are actually in different order than I stacked up our presenters. So, rather than, I'm going to rely on human software rather than on computer software to solve this problem.
We can do this.
So I'm going to go ahead and switch the orders of the presenters a little bit to follow our information.
Do you have slides?
There is. I'd like to save the questions until the very end. And so, yeah, I think we have, so Deva, would you mind pinch hitting here on this one?
Yeah, I'll go ahead.
Or I can speak to it, and you can speak to mine.
You probably can speak to my files. I don't think I can speak to yours.
That's why I love the green group.
Okay.
Everybody's so team-oriented.
Yeah. So, what are the challenges we have for achieving energy efficiency? And there are literally large number, but recently one of the RFIs that was published on the NERC's website, one of the things caught my eyes, and I said, this would be an excellent forum where there are utility companies, facility guys to talk about this challenge. So I'm going to focus only on one challenge. Where do I point this?
Where's it pointed?
I don't know.
I just hit it. You just go ahead. I pointed it there. Yeah, there you go.
Okay, I see. Okay. So I'll skip. So basically, as you saw from the earlier speaker, that if you continue on the path to go to the Exascale, very soon we'll have to build a facility, and right next to it we'll have to build a power plant, right? And that's one of the things. Now, this is, when you think about high performance computing, naturally everybody thinks about supercomputer, but when you are managing big data, financial systems, or even the imaging system that are used in the healthcare, all these places, these portions of the high performance computing is coming into play, right? So it's not going to be restricted only for some specific supercomputers. Portions of it, or in some cases even totally, it will affect all other places. Now, one of the things, as I mentioned earlier, for probably last 11 years, I focused on working on servers, and we said, okay, how do you achieve the energy efficiency? The best thing is make the energy consumption proportional to the load. And not only we, Intel, but the entire industry participated into that. And this kind of chart shows that as the year progressed, basically what happened is the energy consumption started becoming more and more proportional to the load. You can see the idle, which used to be over like a 270, has gone down to 50 watts, and the line has become almost the ideal line, right? So this is kind of a good stuff. And this is not only happening in the processor, but memory, voltage regulators, fans, everything. Anytime there is a lower load, it's going to the lower load. Now, this is good until you run into the high performance computing. Why? In a typical data center, you have, let's say, large number of servers. You have, let's say, 20,000 servers in a room. They're not all busy at the same time. There is a law of averages. There are some busy and some are not busy. So average power consumption, there's not going to be a huge variation. Versus when you are in the high performance computing, you got, let's say, 20,000 nodes. They are either busy or they are not busy, right? So now if you make energy consumption proportional to the load, what's going to happen is there is going to be huge variations. Now, utilities or even facilities, they don't like that. So what they are saying is you need to make sure your variation don't go over a certain percentage over a minute time period. And oh, by the way, if you are allocated some amount of power, let's say 6 megawatts, I don't want you to go down to 3 megawatts, or obviously I don't want you to go over 6 megawatts. So you need to be having a constant power. This goes exactly opposite of what we are trying to do with the energy efficient system, because with the workload, we are trying to vary it all the time. And particularly, you're going to see huge jumps if the machine gets idle, or from idle it starts, or, there are software crashes all the time, right? At the crash time, it's going to go to the lower power. So it's going to be a big jump on the load. So so this is the one challenge that I said I'll talk about. So how do you do this? If the power consumption is going up, we have all kinds of technologies that will either control the rate of ramp or make sure that the power doesn't go over the allocation. But what do you do when the power is going down? How do you control the ramp down without deliberately burning the power? I mean, there are several ways you could do that. Obviously, if there are some jobs that are pending, you can run, that becomes obvious. Let's say, but you don't have anything, you could say, I'm going to just run a job just for the sake of burning power. Or what are the other ways? So we need, and I'm pretty sure there are a lot of ideas that people can come up with, but this is one of the areas that I think we need to start innovating. At the same time, one of the things in that RFI, I found out that there is about 2 hours of negotiation before you change your power consumption. 2 hours in computing, it's a huge time. We need to figure out a way whether we can get a fast response, because that's another good way to manage that. And there has to be some new approaches for allocating the load, allocating the power, and manage this. So I wanted to present this here so that people will start thinking about it.
Great. Okay, thanks. So Woo's told us we're going to a gigawatt, and Deva told us we can't ever turn it off. All right. So let's see. What do we have next?
Okay, sorry.
Okay, George, it looks like you won the lottery on this one. So.
Yeah, this goes forward, this goes back.
It's easier for me to point.
Yeah, great.
So I'll talk very briefly because Wu made an excellent introduction. So the top-notch, most energy-efficient computer tend to be around, Wu call it 2,000 megawatt, megaflops per watt. I call it 2 giga. It's the same thing, 2 gigawatt. 2 gigaflop per watt. It is more efficient by exploiting so-called frequency and voltage scaling. Let me give you an example. Counterintuitively, if I cut the frequency by a factor of 2 for a processor, I actually sacrifice the performance by a factor of 2. A lot of time, my manager told me, get lost. I don't want to sacrifice factor of 2. But wait, how much power you cut? You cut a factor of 8, okay? So if I cut the frequency by a factor of 2, I cut power by 8, in return, I put 8 times the processor, I get even on the power usage. And I get a net win of performance 4 times the floating point operation, 4 flops. And that is what Blue Gene played, the game Blue Gene played, what IBM played on that. Now, in terms of the future challenge, just remember 2 gigaflops per watt. In case you don't know, your Christmas light takes 4 watts. With the 4 watts, I provided you with 8 billion floating point operations. So it is actually already pretty good. But DOE says they want, at 1 exaflop, at 20 megawatts, which means 50. So to jump from 2 to 50, I have to improve 25x. Even if I scale 3 generations of silicon technology, it probably gives me an effect of 8, but not 25. There is your first challenge. Another challenge is we saw 1.2 gigawatt. And this power plant, if anybody can name the place, I'll give you personally $10. This nuclear power plant, each of them produces about half gigawatt. So just put into perspective, okay? And then when you lower the voltage, right now Blue Gene Q already lowered to below 0.8 volts. If your supply voltage dropped to say 0.5, you run into numerous problems again. For one thing, you are more susceptible to the godsend particles from the universe. Soft error rate will go up considerably if you lower voltage. The other thing is leakage current. If your threshold voltage is lower to accommodate lower voltage, your leakage current actually goes through the roof as well. So that's another challenge. Another knob you can turn is you say, gee, another thing you learn in high school physics is power is proportional to some capacitance times voltage squared times frequency. So if you were to reduce capacitance, that is the net wing. So people are now trying to stack chips together in order to reduce the distance and reduce the capacitance. That is a good direction to go. However, that's costly in packaging. Okay? You have to spend money. It's not cheap. And of course, we can play games with CPU. We can also increase the Exascale. The software now is very complex. You have now many, literally millions of processors running simultaneously. How do you harness them and get a good fraction of all the processors running effectively? That is a challenge in software model. Plus now if you have CPU, you have GPU, you have all kinds of heterogeneous computing going on, it is getting more and more complex. And finally, the network, the optics, the storage, all of them present their own challenges. So I'll leave it at that.
Great. Thanks. George? Next, let's see.
All right, so I have 4 minutes to convince you that Exascale is important and we should have the federal government invest in it. And I brought some, just to make sure I don't miss a point, since I only have so many points, I brought some cards here. So as I said, I represent Lawrence Livermore National Lab, who's been in the business of national security for 60 years. Now, Exascale is really not about, to us, an Exascale computer. It's about running Exascale simulations on Exascale technology. That's what's important about it. It's computer simulation. And the US is a leader in computer simulation. I don't think anybody would contest that today. We're a leader in not only the hardware and the software that runs Exascale computers, but the applications on top of that. If you look around the world, people running simulations are often running either on US hardware or software or running US simulation applications. We're a leader today. And a lot of that is a large part due to DOE and the national labs, as well as others, but that's a large part. Now, so you heard some of the problems, right, getting there, and I think they articulated them pretty well, but it's getting harder to program these systems. It's getting harder to buy these systems. They're becoming more expensive. It's getting more costly to operate them, and they talk to you about that. The trends for computing technology are going in a direction that's not favorable to simulation. The market for computer technology is clouds, right? It's mobile devices, right? It's small web servers. So it isn't that these computer technology companies are after simulation, they don't like us. It's because it's not the market. We don't have the volume. Right, so that's the problem. So the benefits I put up there is really simulation is benefiting national security, and we can really use this to understand complex systems, right? And these make very complex simulations where there's a lot of data, they're exchanging a lot of information, hence you've got to run these things all together as a system. In addition, US businesses are using simulation more and more for a competitive advantage. And simulation has matured enough that it is, believe me, it is a disruptive technology in a good way. Simulation is a tremendous advantage if businesses can take advantage of simulation. So we talked a lot of the challenges. I'm not as pessimistic as Wu is. I don't do a straight line. We think that these people are smart enough to make progress. But let me just put a chart up there that talks about the red is how much we pay. The budget, let's say there's a budget up there. I don't know what it is. I can't even read it. Whatever the top is our budget. The red is the amount we pay for in power, and the blue is the amount we pay for in a computer. Let's say we run it over 5 years. So if you're on the left part, we maybe pay 10% in power. So if you have a $100 million budget, $90 million goes to the computer, $10 million goes to pay for the power. As you go along in time, we'll be paying for, with a $100 million budget, or what is equivalent, $10 million for the computer and $90 million to run the power. Okay, this is just an untenable situation. In addition, we've done some interesting studies to show that with a similar budget, the computer that we can buy today and how it performs in our simulation will actually cause our simulations to perform less well. So with the same amount of budget, because of these trends I talked about, buy a computer today, we buy a computer in 10 years, that simulation will perform less. So this is really a problem, and you can't invest in it today and expect tomorrow. If you want to invest in technology, you have to invest way up front to affect change. So why now? Well, I talked about these trends. These trends are causing us a lot of problems. The other thing is there are some national security needs that demand more powerful computers to either run things faster or to run larger, complex problems. And the third thing is, as I mentioned, is that businesses. This is a competitive advantage that U.S. businesses have today in the global economy. And we think this is something that'll be important in the future and could be a game-changing thing for business. And I don't know how to, I have the slide thing. All right. Now, how do we know we're right? Well, you can ask me, well, Terry, you can wait for a bit, and it's not a big problem. But other countries have decided that this is important for them too. Right? So we've heard from the European Union is investing in Exascale, right? China is investing heavily. Russia has said they will. Japan and India. They all think it's important. And Congress thinks it's important. They asked us to come down and brief them last week, asked the national labs to come down and brief them on this topic, and we did. And now they're talking about a hearing and maybe actually funding some of this investment that we're asking for, even in times of these financial woes for the U.S. I think that says something. But while we're not sitting around and waiting, so we actually have made some bets. We've made some initial, you may think they're large, 62 million, but when you're developing a new chip for Intel or a new processor, that's peanuts. But we're investing right now in R&D, so we took money out of our budgets and are investing them with, in fact, these three companies. They're not the only ones, but we invested in Intel processors and memory, right? Reduce the power, increase the bandwidth. We invested in IBM in memory, and we've also invested in Livermore, particularly invested in the processor at AMD. And then we invest in NVIDIA as well because of the graphics processors and storage as well. So that's the $62 million in fast-forward contracts, which they're meeting at Livermore right now, these 3 days. We're also looking at investing, making very particular target investments in system architecture for supercomputers. These are things that people don't normally invest in for just the normal markets. And we're looking to buy some big computers that we hope will force the businesses or encourage them to move in a direction that's more friendly to simulation. Now, the final thing I just want to mention is that these things we're investing in, they're not some special high-performance computing processor, right? They're not some special memory that only will be bought by us. They're the technologies that will go in to their mainline products. It'll go into consumer electronics. It'll go in their IT hardware and software. U.S. businesses will buy this and use it. So if we can help them accelerate bringing the power down and making these things more cost-effective, the whole entire business will benefit. But we've done a little bit now. We need more. And so that's why we're off, trying to get Congress to pay some attention to us.
Great. Thank you, Terry. And Alan.
Guess I'll back clean up today. My colleagues have said a lot of interesting things, and I agree with most of them. We do have these challenges. I particularly agree with the importance of hitting Exascale, and for the same reasons you mentioned. I think I'll shed a slightly different perspective on that. Exascale is something it's fantastic. I mean, it's fantastic, as we pointed out in a couple of ways, in a scary kind of way when we talk about power. But what it's going to enable this world and the people in it to achieve is truly fantastic in a wonderful way. And then I know that's why many of you are sitting here today. And the goals, whether it's security, whether it's, what it's going to do, for the world, for the environment, for being able to feed the people of the world, protect the people of the world, enable us to achieve things we haven't even thought of. It's amazing. But what I want to talk a little bit is the importance of the path there, because we frequently talk about, we're here, and Exascale is here. And I want to talk at least a little bit about the path there, because I also think the path and how we achieve it is going to be very important. Whether it's industry, whether it's academia, whether it's the government sector, I think it's important that we all pull together in a variety of ways. I mean, certainly, modeling and simulation, that's the one that really sticks out, for me as well, as an area that, whether you're in industry, whether you're an academic, or whether you're in government, this is so important to us these days. And we need to look, again, not just at, exascale systems, because I talked to some folks about exascale. I'm sure we have the same problems in our own companies, whether you work for a semiconductor manufacturer, a software company, and say, oh, we're not here yet, and call us when we are. But it doesn't work that way. We need to think about the path there and how we're going to get there in order to be effective. To achieve these types of things, using, advanced models, things like that, I think it's important to realize where we are today. We've just now entered, I picked up about 10 business magazines. My friend and I were at Barnes & Noble a couple of days ago, and we just picked up 10 business magazines at random, and we looked in them. And when we did, we looked at some articles, and they were interesting for the first time because they were talking about big data. And big data is an exascale, and we all know that. But one of the interesting things about of the articles that we found on big data, half of them mentioned that, and this is certainly new to me, at least in terms of reading it in the common press, is that not only we're looking at big data these days, but we're really starting to begin to look at the uses of big data and how we're going to manipulate it and how are we going to use it and how are we going to manipulate it and mold it to our will to do a bunch of interesting and, again, fantastic things that we haven't been able to do before. So when we look at that and we say, okay, well, now we have big data. What comes after big data? Well, the logical thing, and a term we've been using, which hasn't come into the common vernacular yet, is big compute, right? In the old days, it was, sorry, I guess I should lean forward in order to be heard. You'd have your standard commercial things there, and your HPC systems were here. As we've moved along in time, those have tended to converge. They'll probably never converge, certainly not in our lifetimes. There'll always be something new and big to strive for. But I think it's important to realize that they're a lot closer together than they used to be. I ran a modeling and simulation workshop along with national laboratories in, I guess it was March of 2012. And it was interesting to see one of the folks who was talking there from Procter & Gamble was talking about how they're using a lot of these big compute models and simulation to decide how to make toilet paper and put it on the roll. And you say, well, what do you need, this massive supercomputing to do that for? Well, because if you can just shave a fraction of a millimeter of paper off of it, and you think of how much that's used throughout the world, and then you want to sell throughout the world, that can end up being millions of dollars back in the corporate pockets. So it's important to think of, we think of these big and lofty ideals, but it gets down to simple things like toilet paper. It gets down to simple things like tires. It gets down to simple things that people need and use every day. And the path to exascale is what's going to enable that. I wanted to talk one other brief thing about what we're doing currently at AMD, at least an approach to that, and that's heterogeneous computing. We announced last year that we brought on the ARM architecture, so now we have ARM architectures and x86 architectures and GPU architectures put together in what we're calling APUs, or accelerated processing units. We started the HSA, or Heterogeneous System Architecture Consortium, which enables one to use these APUs in a broad variety of new ways. But the importance of this is that, rather than saying, okay, I need a system of this type or a system of another type, flexibility, particularly for businesses, is becoming increasingly important. Like, for instance, in the old days, you either had a server or you didn't have a server. Nowadays, you're seeing a lot more flexibility in that. You might need truly an all-GPU solution. You might need something that's truly heterogeneous. You might need something that is strictly a big data solution, or you might need something that's involving more and more compute. And when you look at heterogeneity and you look at groups like the the HSA Foundation and others that are trying to put forward ways to use this, it really gets back to a fundamental problem we're talking today, which is, of course, power. Because when if you think of one size fits all, you're not going to get there, and you're not going to have an effective path. If you start thinking about how can I use this for the types of problems that we're using, and how can I either statically or dynamically mold that, either through the hardware or the software, how can I move the things that I want? Do I want to move the data to the compute to the data? How can I do that in a very power-efficient manner? That's really what heterogeneous computing is about. And thinking about that as we get on this path to exascale, I think is critically important for us.
Great. All right, well, thanks to our speakers for giving us that great introduction. I think, you could take either a pessimistic or an optimistic view of this thing. The pessimist view is that we're going to have to use a gigawatt that we can't turn off. If we can get that factor of 10 in frequency, we can get there at efficiency, but there's no way to do it because of physics. And because of that, we're going to spend all your tax dollars on electricity. Or you could take the optimistic point of view, which is we will figure out how to get the factor of 50 that we need in computational efficiency. And oh man, I made these notes here. It's going to take major innovation in how we manage workloads in these big computers to make them respond effectively on the grid. It's going to take huge technical advances not only in compute nodes but in networking and storage to deliver the full-scale solution that'll enable really new capabilities not only for our national lab simulations but I think for all kinds of business innovation in this country and around the world. But I think that our solutions that we're going to develop, as Alan pointed out, are going to be really respond to even greater and greater diversities of the kinds of workloads that they process. Optimist or pessimist? I'd like to hear from the audience a little bit. What are your questions? Do you have questions for our panelists about what you've heard today? We have some mics, but I think we hid them. So if you, Michelle's got hers back there, and she's going to start with Jack in the back, and we'll just work forward that way.
Yeah, so the hecklers go first. I think it was 2018 was the target time frame we were talking about to hit this. You're going to get there by 2025 according to Moore's law anyway. So why are we worrying?
Maybe I could buy one, but I don't think I can afford it to run it, and I don't think I can run on it, and I don't think I can get my codes on it.
The other thing is I would say that we'll get there in terms of Moore's law in the sense that the number of transistors per area is going to continue to double. What's not going to continue is this notion of Dennard scaling. We're not going to be able to increase the frequency by 40% while maintaining the same power density. And that's really what the issue is, not so much Moore's law.
Well, of course, you're all, in your mindset, sticking with silicon, and there are other technologies as well that are out there that are being looked at. So whether it's 2025 or 2030, it's going to happen. And it's just a matter of, is it going to be bio? Is it going to be silicon-based? Is it going to be some other architecture? So I think this discussion that I'm not hearing from this panel is where's the investment, where's the R&D into some of the other technologies and other sciences that might get us there. I think it's great that we're pursuing it. And 2018's, pick a date, doesn't matter. I think it's great to push it, but I think we need to look beyond silicon perhaps to find the answer to that. Anyway, it's just one data point.
So I give a little flippant answer, but I think you'll get it. I mean, you're right. It depends what you're going to use it for, right? And so I think pursuing all those other avenues of investment, I think is going to be useful and is going to be necessary. But you have to look at the simulation isn't just about the computer, right? It's about the application. And these applications, if you give me a quantum computer, right, or a biocomputer, these are very complex, million lines. There's probably, I would say for some of our codes, you could probably in today's money put there's like $1 billion of investment in that code. And so you can't just take that and rewrite it for a very different computer. So we need to evolve these things or we throw it all away. And so we need a path that's evolutionary but gets us there and not not just seek out a revolutionary path, at least for us. But I think you're absolutely right for other uses that could be a really good path to follow.
Yep, great. Let's see, we had some questions up here in the front. Michelle, over here on the right and on the left. Oh.
On? Yeah, okay. First of all, thank you to all the panel members. Question for Dr. Wu. I'm still trying to analyze all the charts you put it up there. Going back to first chart, I'm not sure if you can bring it up on the thing. I'm trying, again, we need a big data center to analyze all the things you put up. But based on I'm trying to see what we can get out of what you are saying about the top 500 and the first quadrant moving fast, the rest of it is not. Can you tell me what is your thoughts on that? First of all, you're not measuring the same 500. What you're measuring today, 500, are different set of computers than 4 years ago.
Yes.
Yeah.
So
Yes.
we got to be careful about that.
Oh, yes.
And the number 1 4 years ago is number 281 now.
That is correct.
Right.
Yeah.
So we got to be very careful
Yes.
as how we present them. But
Yes.
with everything said and done, we all understand that. What are we getting out of this data? That top 25% are increasing the efficiency,
good
bottom 25% is not.
That's a good question. I mean, the very first chart was just to really get an understanding of how we as an industry, a community, are improving in terms of our energy efficiency. And the first chart that you're referring to, I'm assuming, it's the one where I showed that the first quartile really it's improving exponentially. And that's, I think part of that is to show that if we focus if we focus some of our efforts and investments, like Terry was getting at, is that we can get to these projections of 67 megawatts to 100 megawatt systems. If we continue to kind of look more at the standard commodities that are going on, we're going to get more of an improvement along the lines of what you see in those green boxes. It's going to be more of a linear improvement in energy efficiency. And that's part of, and Terry can correct me if I'm wrong, I think this is part of the reason for the investment in the fast forward projects, is to see if we can't move things forward in a way that we can make the norm be more what's out on those outlying dots rather than what's going on in the green boxes.
Still have to digest it, yeah, sure.
Well, another thing to look at is that when I was doing the projections here, I was actually picking the most favorable machine when I did the projections here. Okay, and back here, so that means that the projections I was making are based on the machines that are at the very top.
Yeah.
I'm not even looking at the ones down here. It's worse if I were taking a look at it farther down on the list.
So on the other side of that, especially to Terry's point, if you don't want to change the programming model, the information I saw from Lawrence Berkeley is that to get to that goal of the Exascale currently, they're showing 70 to 100 kilowatts per rack to achieve that. And nobody talked about hosting that in a data center and how you're going to cool it and power it, et cetera. There's a whole bunch of challenges that you're forcing somewhere else by having that programming model that you can't get out of. So I think to Jack's point, you got to change. You almost have no choice. And there's going to be changes across the board. And I think the only one who really addressed it was George from IBM, showing that it's going to affect networking, optics, the packaging. It's not just CPU.
That's right.
I mean, it's the whole ball of wax.
It's an architectural
and
question.
The whole ball of wax isn't even what he showed. It's also the programming models, the application design and architecture, corporate culture, legacy stuff. You got to address all of it to make something like this happen. And yeah, you're going to be able to answer new questions, but just like going to the big data stack, People threw out their Teradata data warehouses to go to this new open model of Hadoop to answer new questions with a new style. The same thing is going to happen here.
So you're absolutely right. And I would say the Exascale program that we've envisioned is not just investing in the competing companies. It's also investing in software. It's investing in the whole, and the applications as well. And the applications, you know, they have to change. You're absolutely right. But we can't put a new program model and say you have to change tomorrow. You have to stop what you're working to reprogram your entire application and rewrite it in this new program model. There has to be a path that evolves. I mean, we went from, you know, mainframes to these codes to vectors, from vectors to MPI, message passing. Now we're taking the next jump to something, right? But we can't expect them to do it overnight. It'll take years to get them there. So we need to provide a path that they can evolve, right? And some of the other, I mean, like the GPUs, which we can't really use efficiently now, but others can. That's like a technology that other applications can get to and use effectively, and then we learn from them, and that's great. So I agree with everything you said, and if you ever get a chance to come out of the living room, we'll show you what we're thinking about in the facilities.
I completely agree as well. I mean, we're taking a holistic view on some of our own research that we're doing. I'm just presenting to stir the pot a little bit what we have seen trend-wise on the Green 500. But there's a lot of work that we're doing, for example, in the runtime system, so that the hope is that people can keep their same programming model, and that the underlying runtime system will figure out adaptively at runtime, underneath the hood, where to best dole out the tasks for performance efficiency as well as energy efficiency. So the idea is say, oh, well, you know what, I have something that's more vectorizable. I can run it on simpler cores, like a GPU or the many integrated core that Intel is doing. Yes. Okay. So I mean, those are certainly things, you know, take a more holistic approach to it. It's not all going to come from one place. You know, just the runtime system work that we've done. This is a biased view. Is we've taken OpenCL codes that you would just run on your typical CPU and GPU, but at runtime system we'll figure out automatically how to dole the work out, and we can get an additional 8-fold performance improvement, and hence 8-fold better performance energy efficiency given the thermal envelope that we're running under. But it takes a lot of work and a lot of investment of resources, and you know that's a fairly large funded project that I have going on that's, you know, separate from the Green 500. But I just wanted to give a perspective from the Green 500 in terms of what we're seeing trend-wise.
Brad?
So to put in a shameless plug, we hope that you enjoyed the idea of talking about Exascale here, because the reason that we put the panel together is the U.S. Coalition for the Advancement of Supercomputing came to us at the Green Grid and said, hey, could you help us work on this problem? So if you're really interested in this, as we're putting the AR together to take this to the board, you can send me a note. You know, I'm out on the Green Grid website, Brad Breck, and I'll make sure that as we're putting it together, we contact you to get you involved, because that's one of the reasons we're here together, is to get involved with solving some of these problems. So if you're interested, step up. I know John will appreciate you stepping up to work on it.
So I'd like to add to that, and also what Terry talked about earlier. So when there was something that happened about a decade ago with the Japanese Earth simulator that people viewed as Compute-Nick. I'll play on words, Sputnik, what happened with Sputnik. When the Japanese Earth simulator just shattered you know, the records in terms of being the fastest supercomputer. I bring this up because what happened after that, 2 or 3 years down the line, there was a very broad study done about the importance of high-performance computing to companies out there. It was done by the U.S. Council on Competitiveness. And they found through this survey, and there was several Fortune 500 companies on that list, they found that 97% of the companies that were surveyed could not exist or they could not compete without high-performance computing. And so, I mean, I think you saw a little bit of that. I mean, you don't really look necessarily at Google as a traditional supercomputing company, but this morning you saw supercomputing-like facilities. Okay? So tackling this problem of energy efficiency is an important one because it'll underpin a lot of what companies are needing to do in terms of high-performance computing to solve their problems and stay competitive in the work world.
And I like to reiterate what Brad was pointing out. And one of the things we did not do here is necessarily list all the areas where there are opportunities. I'm turning challenge into opportunity. But this gentleman mentioned that we're talking about a 100 kilowatt rack. I mean, right now, lots of facilities managers, they would have lose their sleep if they have to install 15 or a 20 kilowatt rack, right? Now, all of a sudden, we are looking at 100 kilowatt. Imagine the kind of revolutionary or innovations they will have to go through in order to even build a 100 kilowatt rack, support it there, manage it. Even there are challenges. There are a lot of people involved here in the DCIM kind of solutions. You talk about in-band solution versus out-of-band solutions. Here, we are trying to manage the workload. There is itself going to be a lot of debate. I'm just pointing those things out is so that a lot of people will get involved into this, start thinking about the opportunities, and come up with an innovative solution. We all need to step up in order to achieve this.
Any other questions out there in the audience? How much time do we have, Michelle? Oh, we got 3 minutes left. Well, that's a perfect amount of time to tell a joke or wrap up the session.
Wait, we've got a question.
We got a question, great.
Now, and did you guys talk about the possibility of co-locating the power plant with the data center? Move it in the fracking zone, perhaps?
I know like NYSERDA, what is it, the New York State Energy Research and Development Authority. Hey, I got that right for once. I know they've been doing some work with Clarkson University and things like that. But this gets back to, I didn't catch the gentleman's name, but the exact same thing. We've been looking at everything from low-level circuit techniques to save power all the way up through programmability, things that look at, chassis improvements to fabric improvements to actually physically putting things next to green energy such as dam hydroelectric installations, windmill installations, et cetera, to try to, keep chipping away at different portions of this problem.
And another way also, again, this is the innovation that we need to bring in. I talked about the problem about managing the ramp here, right? Now, utility companies sort of do that, not at the time scale we would like to see, but they have, power generation which stays up and cannot be changed for something like weeks, maybe a nuclear power plant, right? Then there are other power plants that they can fire it up as they expect the load will go up in next few days or hours kind of stuff. Maybe in order to manage, if you want to manage the RAM, not only we need to think about regeneration of the energy, but having a small plant in the facility so that whenever you are increasing power or when your power consumption goes down, instead of having to start making demands on nuclear power plant, you shut down your own power plant, right? So there has to be some different way of, we need to think to figure out how do we satisfy to have exascale computing, stay within the power limit, and also don't affect the power quality of every other user that's on the planet.
Yeah, so this isn't really answering your question, but I have a little bit of tidbit. We recently formed a collaboration with the three largest utilities in California: PG&E, San Diego Gas and Electric, and gosh, I'm terrible. I can't remember the other one. To work on to apply computer simulation to their problems. So looking at grid problems, grid safety, grid efficiency. How do you include renewables in the grid? And so we're actually trying to apply simulation to solve their problem. And it's about $150 million for 5 years that we're going to help them with. So.
Yeah, it just, as an aside, both Qualcomm and UCSD have big steam or big gas turbines and then chillers that are powered by the waste heat. So that, that's probably what you have to do when you get up to this many megawatts with variable power, that that you mentioned.
Great. Okay, so I'd just like to summarize that, we've had a brief introduction here to the exascale computing problem. I think it's a huge computing efficiency problem, probably the biggest one I think we've ever faced. If we can solve it, it'll be a driver not only of our simulation capabilities of the national labs, but I think a huge driver and competitive advantage for businesses worldwide. And if you have interest in participating with that, we, as Brad mentioned, and I forgot to mention, that we're going to be working with the Coalition for the Advancement of Supercomputing. They've requested the Green Grid's help in thinking about the broader implications of these kinds of efficiency questions, and we'd encourage your participation with the Green Grid as we start moving forward with that collaboration. Thanks to our panelists for their participation with us today.